I'm an idiot. All right, so anyway, section 7. So we've talked about the beginning of the universe, the beginning of the solar system, Earth, and its different layers, what's going on the inside. So let's talk about what's going on the inside and how that affects what's going on the outside of Earth. And all of that is encompassed in plate tectonic theory. Theory, highest level of knowing. All right. So the Big Bang theory, the nebular theory, plate tectonic theory. Come on now. Okay, so let's first talk about a term called convection. Whether you've heard it or not, you've probably all seen it. As you go to boil a pot of water, you want to make some delicious macaroni and cheese. The way that works is through convection. Heat is transferred to the pot. The heat is transferred from the pot to the water. When the water heats up, it rises, and as it cools down, it sinks. That's why it's called a rolling boil, because that's essentially what the water does. All right, so whatever's closest to the bottom of the pot gets heated up, because that's where the heat is. As it gets further away from the bottom of the pot, it cools down. Hot stuff rises, cold stuff sinks. When we're looking at the same material, when we heat some of it up, the hotter stuff will rise, the colder stuff will sink. That's how a hot air balloon works. So it's just filled with air. But when you heat it up, it becomes less dense, so it will rise. Things that have a lower density will rise. Things that have a higher density will sink. So, convection, again, is a form of heat transfer from one medium to another that forms some sort of current. And it's usually where hot stuff rises and cold stuff sinks. Well, guess what? That's what's going on inside the Earth. So we have some heat source within the Earth. Ooh, that was a fancy little graphic there. So we have again, leftover heat from the formation of the Earth that's been trapped there. We have radioactive decay that's going on. We have stuff moving around, so we have friction happening. You rub your hands together, all right? That generates heat. So we have these heat sources that are within the Earth. So inside of the Earth is hot. The core is the hottest. The heat from the core, inner core, solid inner core is transferred to the liquid outer core. The heat from the liquid outer core is transferred to the mantle, and the mantle then transfers that heat elsewhere. So, when the mantle material is heated up, so the mantle, again, mostly peridotite, when some of that is heated up, the stuff closer to the core, which is going to be warmer, then that hot mantle material will begin to rise. Remember, it acts like, the mantle's like hot, sticky Play-Doh mixed with rocks, if you can imagine that. So there's some movement to it. Slow, but it moves around. So hot mantle material rises. As it gets further away from the core, it cools down and it sinks, and that process happens over and over and over again. That's called mantle convection. Go figure. But what happens when that hot, sticky Play-Doh mantle material interacts with the plates and crusts above? Right, when that hot mantle material is kind of creeping up, I don't know why I'm so off center. When that hot mantle material is creeping up, it grabs onto those overlying plates and crust and lithosphere and can pull it apart as that material cools and sinks. Or in other places, it might actually kind of crash plates together or kind of do a number of different things. So what's driving all of the movement of the tectonic plates on Earth is this process called mantle convection. And it's the key to plate tectonic theory. Funny thing about plate tectonics, we didn't know how all of this worked up until about 70 or so years ago. So some of your grandparents or or even parents, depending on how old you are, had no idea how the Earth worked, because plate tectonics is the driving force of geology. It's what causes volcanoes and earthquakes and some mountain ranges and any number of things. And if that's what's driving geology, and geology is connected to weather, and it's connected to the water, and it's connected to biology, so up until about 70 years ago, we didn't know how any of the hell of this worked. Can you believe that? We get more into this in Physical Geology 101 if it's of interest. But for now, just know that this process of mantle convection occurs. And so you get this upwelling of mantle material. Again, it's heated up from the core, from the heat from the core that radiates into the mantle, and it can pull plates apart. Or in other places, it might crash them together. Sometimes tectonic plates are made up of continental crust, thicker, less dense. Sometimes they're made of oceanic crust, thinner, more dense. Sometimes it's a combination of both. But it's mantle convection that is driving plate tectonics. So the lithosphere, the solid part of the Earth, the crust and the solid upper mantle, is broken up into individual pieces or plates, called tectonic plates. Plates move over the asthenosphere, that's that kind of plasticky layer of the upper mantle. And all of that is driven by convection cells. It's driven by mantle convection. One way to kind of think about mantle convection that works for me is imagining a lava lamp. I don't have one in here anymore. But if you've ever had a lava lamp, all right, the way it works, it's plugged in and there's a light bulb. One of those old school light bulbs with a filament that gets real hot. LED bulbs, they don't get hot, so lava lamps don't work with those, but one of the old incandescent bulbs that get really hot. So the heat source, the light bulb, radiates heat into the glass container. There's actually a little metal wire at the bottom of a lava lamp. So it transfers heat to the metal wire. The metal wire transfers heat to the lava, which is just wax, like candle wax. And the candle wax and the surrounding oil are very close in density. So that when the wax heats up, it becomes less dense, it rises. And as it gets further away from the heat source, the light bulb, it cools down and it sinks. So what's going on inside the Earth, these convection cells, is very similar to what happens to a lava lamp. There's a heat source, heat's transferred to the lava becomes less dense, it rises, and it gets further away from the heat source, it cools down and it sinks. Same thing in the mantle. It's mantle convection. And all that moving mantle material is what is driving plate tectonics. It's what's moving all of the plates around on the Earth. So here's a modern map of the different plates that the Earth is made up of. There's a handful of major plates, big major plates, and a bunch of smaller little ones. For instance, we sit on the North American plate. Here in Arizona, we sit on the North American plate. Then we also have this very large Pacific plate. There's this small little Juan de Fuca plate that's actually crashing into this part of North America, which is responsible for a lot of volcanoes and earthquakes in Northern California, Oregon, and Washington. For instance, Mount St. Helens that erupted in 1980. That's due to this small little plate crashing into the North American plate. But we have, again, some major plates and some smaller ones as well. And they all kind of jostle around. Sometimes they crash into each other. Sometimes they're kind of pulled apart from one another. Sometimes they kind of slide side by side next to one another. Different hazards are associated with those, but all of that is driven by mantle convection. So with the boundary of those plates, the edges of those plates, they're usually kind of marked by volcanic activity or earthquake activity. That's how we can figure out they're there. That's how we can figure out where plates are interacting, because at that boundary where one kind of meets the other, whether it's crashing in or pulling apart or kind of grinding side by side, we can get volcanic activity or earthquake activity. Depends on the type of boundary. It's crashing together, pulling apart, or sliding side by side. But that's how we can usually tell there's a boundary there. For instance, in California, there's a lot of earthquakes. Why? Because it sits right along this boundary between the Pacific plate and the North American plate. These two plates are actually grinding in that area, side by side, which creates a lot of earthquakes. Not a lot of, almost no volcanoes in this case, in this part of Southern California, but a lot of earthquakes. So that's how we can kind of tell where there's the edges of plates are, areas that get a lot of earthquakes or volcanoes. For instance, on the east coast of the U.S., there's no plate boundary. The closest plate boundary is kind of way out here. So guess what the East Coast does not get? Earthquakes and volcanoes. Why? Because it's not near a boundary. So anyway, that's how you can kind of figure out where the edges of these plates are, where these boundaries are. Again, at these boundary plates diverge, so they move away from each other. They converge, they crash into each other, or they slide sideways past each other, and that's called a transform boundary. Little image about these different boundaries and kind of where you can get different things. So a divergent boundary, these plates are moving away from each other. So you can get some volcanic activity, very weak earthquake activity. You have, for instance, convergent boundaries. It looks like for instance, this plate is colliding with this plate, and so this is a convergent plate boundary. So different boundaries, we see different geology based on what type of crust is interacting, continental crust, oceanic crust. So we get into different hazards. Again, that's more so Geology 101 and 110, natural hazards and disasters. But again, mantle convection is the driving force of plate tectonics, and it's this evolving Earth and this changing geology that we're trying to understand in historical geology. So the influence on the geologic science of plate tectonic theory is absolutely revolutionary. Again, it's only 70 some odd years old. The idea is older, but the proof and evidence wasn't secured until about 70 some years ago. It's really a major milestone, really comparable to Darwin's theory of evolution. More on that here in a little bit. And it provides a framework for interpreting many aspects of Earth on a global scale, our understanding of earthquakes, our understanding of volcanoes, how things work, how things change, all came about because we finally figured out a driving mechanism for plate tectonics. We figured out mantle convection was going on, and how all that works. So it starts to relate many seemingly unrelated phenomenon. Now we have a mechanism of relating the Earth to the geosphere to the hydrosphere, because if we have stuff moving around, that influences oceans and ocean currents, which then influences the atmosphere and weather situations, which also then influences the biosphere, right? If different weather, different climate, different things grow. So if all of that's changed over Earth's history, then things have changed, things evolve. All right, so evolution isn't just necessarily a biological thing. Things change, things evolve. The universe has changed. The solar system has changed. The Earth has changed. That's what things do. They change. So plate tectonic theory, again, has really helped us to interpret Earth's history. Now we know the driving force behind all of this. So what's the impact now that we understand of plate tectonics on Earth's systems? So for the solid Earth, plate tectonics is driven again by mantle convection in the mantle, and it's what drives mountain building, volcanic activity, earthquakes. What drives the rock cycle? More on that in a later unit. How it's connected to the atmosphere. Again, if plates move around and continents move around, so the arrangement of continents affects how the Earth is heated and cooled. Therefore, that affects wind patterns and weather systems. So where things are affects weather and climate. We can also get release of gaseous material, mostly from volcanic sources, into the atmosphere, which can change the climate as well. So as far as the hydrosphere is concerned, again, where the continents are, where the plates are, affects ocean currents. Excuse me. It also affects ice and the Earth's ability to have it. And then the biosphere, again, if all of these things are different, if we have different weather patterns, that creates different habitats, that gives the opportunity for plants and animals to migrate to other places based on where things are at. So the biosphere is different as well. All right, so that's kind of the plate tectonic theory, one of the big four theories, and then the next section we'll get into the theory of evolution. Yeah, but before we do, let me give you the super secret code. The super secret code is 2222. 4 of them. 2222. 4 twos. Make sure to continue to watch the other videos. Alright? There's additional information I'm going to give you, but that's the super secret code. I'll see you back here in just a second.